let's talk about specific heat and specific heat capacity in these notes. All right, hopefully this summer you got to escape to the beach at least one day, hopefully. And if you did, imagine your day at the beach, right? So you get there, it's nice and warm. It feels, on your skin, it feels nice and warm. You kick your sandals off, you get in the sand, and ooh, ouch, it's hot. You're like, all the way to your spot, right? You throw your blanket down, stand on your blanket, right? It's a little cooler. And then you get ready to dive into the water. And the water is cold, or at least colder than the hot sand and the warm air, right? So we've got three, different types of matter here. We've got the sand, we've got the water, and we've got the air, and they're all at different temperatures, right? But they all got the same amount of energy from the sun. They've all been warmed by the sun for the same amount of time. So why, oh why, do we have such drastic temperature changes between the air, the water, and the sand? Well, the answer to that is what we call specific heat capacity. All right, fancy term here, specific heat capacity, okay, is the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius, okay? So if we just think about, before we get into numbers, if we just think about the air versus the water versus the sand, okay? Remember, the sand is hot, right? So that must mean that it doesn't take as much energy to heat up the sand, right? Because it gets super hot super quick, right? So the specific heat of sand must be really low, okay? Versus the water is cold, right? It's actually warmer than it was last year, but it's still cold, at least to me. So water must have a really high heat capacity, means it takes a lot more energy in order to heat up water than it does sand, all right? And then air's got to be in between, okay? So we can even just kind of take a step back and just think about the difference between the two and figure out, hey, this one, the sand must not require as much heat energy to heat it up versus the water. And that is exactly what we see when we take a look at the numbers. Okay, so if we take a look at the specific heat capacity for the sand, look, we predicted it to be a low number, and boom, it is. It's only 0.8 joules per gram degree Celsius. Joules, we're going to find out, is a unit of energy. Okay, so calories is another unit of energy. You've probably heard of calories before, because that's the unit of energy that is used to measure the energy in food. Okay, joules is similar to that. So the specific heat of sand is only 0.8 versus water. Water takes a lot more energy in order to heat up, and that's exactly what we predicted as well. Water is 4.2 joules per gram degree Celsius. So it takes much more heat, right, to heat up or to change the temperature of a gram of water versus a gram of sand, right? So sand has a small specific heat, so it doesn't take much heat to increase its temperature, right? That's why it heats up so quick at the beach. And if you stay long enough at the beach to let the sun go down and some of that energy to be released back into the atmosphere, you're also going to find that the sand is going to cool down a lot quicker as well. It's able to release that heat. Okay, so that's why the sand gets so hot during the day and cools off at night much more than the water does. The water stays at pretty constant temperature during this day and night because it takes so much more heat to change its temperature, and therefore kind of holds on to that heat as well. All right, let's take a look at another example. So this is the specific heat capacity of water, and now we're going to talk about it in terms of calories. So like I said, joules is one type of unit of to measure energy. Calorie is a different unit to measure energy. They're still both measuring energy though. All right, I need to speak about what this little c means. The little c stands for specific heat capacity. Okay, so C is specific heat capacity. Okay, so we're going to be working with a mathematical equation soon, and so you're going to see this variable C, and you're going to be like, well, what does that mean? It means the specific heat capacity for the substance. So for water, the specific heat in terms of calories is 1 calorie per gram degrees Celsius. And that should be a little degree sign, but the formatting gets screwed up when I put it into this program. In any case, let's take a look at this example. So we have water, which has a specific heat capacity of 1 calorie, versus aluminum, like the can over here, that has a specific heat of 0.2 calories, right? So which one has a higher heat capacity? Okay, so higher heat capacity is the one that has a bigger number, right? So water is able to hold 1 calorie per gram versus aluminum, which is only able to, hold 0.2 calories per gram. All right, so it takes 5 times more heat to change water's temperature than to change aluminum's temperature. Okay, and so we can see already that there is a difference between all kinds of different types of matter, right? Between the elements and compounds that make up the things of this world. So we can relate heat capacity to thermal conductivity, and we've started to study both of these concepts in the last couple of activities that we did with thermal conductivity and also our Cheeto lab, right? So heat capacity is related to thermal conductivity. And remember, thermal conductivity is the ability to transfer heat to or from a substance. So if something has high thermal conductivity, it's able to transfer a lot of heat quickly. If something has low thermal conductivity, then it does not transfer heat very quickly to or from the substance, right? So if we think about it in terms of heat capacity, high heat capacity substances like water are going to heat slowly and cool down slowly, right? So they are going to have low thermal conductivity. Because if we think about it, if heat goes in slowly and out slowly, right, it's not that heat is not moving super fast. All right, so it has low thermal conductivity and is going to transfer heat slowly. All right, these guys are not good conductors of heat energy. Okay, so water, not a good conductor of heat energy. If you want something heated up quickly, you're not going to choose water as your substance. It's going to take a long time to heat it up, right? Just like in our calor y frio activity, right? Between the quarter and the plastic bottle cap, right? The one that conducted connected heat much slower was the plastic little bottle caps, right? So plastic has a higher heat capacity than the metal quarter. Now the metals typically have low heat capacity, right? So think of metals like aluminum, right? Or like the quarter. Low heat capacity substances heat fast and cool fast, right? So they heat up real quick, they cool down real quick, right? That means that they can transfer heat fast, right? They have high thermal conductivity or fast thermal conductivity. They transfer heat fast. And so these ones are good conductors of heat energy, absolutely. If we want something to get heated up real quick, we're going to choose something that has a low heat capacity which means it has high thermal conductivity and heats up, cools down super fast. Okay, so that's how those two concepts are related. Specific heat and thermal conductivity. If something have high specific heat, it's going to have low thermal conductivity, and it's going to be not a good conductor of heat energy. If something is low heat capacity, okay, like metals have low heat capacity, then they are going to be heated up or cooled down quickly, and they have what we call high thermal conductivity. So these guys are good conductors. So let's take a look at an example from real life, right? So we gotta cook, we gotta eat, we need energy for our bodies, we gotta eat. So if we have to eat, then we gotta cook, right? Or somebody had to cook the food that we are eating. So what kind of items do we cook with? So let's just do an example of spaghetti, nice easy spaghetti. Well, we need pots and pans, right? We need water, and we usually have a wooden spoon available to kind of stir things up with. If we think about in terms of thermal conductivity and specific heat, why are our pots made out of metal? Okay, like we just kind of investigated, metal has low heat capacity, right? So metals have low heat capacity, so they transfer heat super fast. All right, so if we, had tried to, make a pot out of wood or plastic or something like that, it would not conduct heat to the water as fast as the metal pots. Okay, so the metal is going to conduct that heat from the flame to the water a lot more quicker than any other substance. And that also means, right, if you touch the metal pot, you are also going to get that heat transferred to you really quickly. So a lot of, if you've ever touched a metal pan on the burner, it hurts, right? Lots of energy going to you very quickly, not a good thing. Okay, so what do we do in order to avoid that? We have cooking utensils, right, that are made out of wood or plastic, right? And the reason why, they suck at transferring heat. They have high heat capacity, so they don't transfer very fast, right? And that's a good thing. We want that, because if it did transfer super fast, and we touch those as well, we would get burned. So cooking utensils are made out of wood or plastic, so they won't burn you. All right, so we got a little bit of thermochemistry here in action. All right, so we've been talking about heat transfer from objects, fast versus slow, high heat capacity versus low heat capacity. Now we're going to jump to the next topic and talk about how we can actually calculate how much heat is absorbed or released from an object. So if we took a cup of sand from the beach and a cup of water from the ocean, right, we could actually calculate how much heat would be absorbed, okay, from it to raise, its temperature. And this is the equation that we talked about in class today in our Cheeto Lab Part 2. Okay, so you need to put this in your brain. You need to definitely memorize, all right, store this in your brain, this equation. Q equals mc delta T, or in this case, m times delta T times C. Okay, so let's take a look at what each of these components means. So Q is the heat transfer. That's what we want to quantify. It's either going to be in calories or joules, because remember, that's the energy unit there, okay? M is mass, all right? So in order to figure out how much heat is absorbed or released from an object, you need to know how big the object is. Something small is going to not, is going to be able to not hold as much heat as something big, right? So we need to know the mass of the substance. Now, delta T, okay, this guy here, delta T is the change in temperature. That's why it's got the little delta sign or the triangle in front of it. All right, so anytime you see a triangle in front of a variable, it means the change in temperature, right? So that means we need to know the final temperature that the substance reached, and we also need to know the initial temperature that the substance reached. So when we were doing our Cheeto lab, we took the temperature of the water before we lit the Cheeto, and we took the temperature of the water after we lit the Cheeto, because we needed to find the difference in temperature or the change in temperature in order to figure out how much heat was absorbed, right? Because if we have just a small temperature change, we're not, not a lot of heat went in. If we have a huge temperature change, a lot more heat went in, right? So we need to know the change in temperature. Now, finally, we need to know the specific heat capacity of that substance, and that's what C is, right? The specific heat. We just talked about that. That's going to be different for every substance, okay? So it's unique. The specific heat of a substance is unique for every different type of substance. All right, we've seen before, right, that sand had a different number than water. Water had a different number than aluminum, okay? Aluminum's going to have a different number than wood. Wood's going to have a different number than air. So we need to know the specific heat for that particular substance. So a lot of times we have to look that number up, all right? In your case, it'll be given to you in the question, so you don't need to really worry about that. All right, so Q equals mass times the change in temperature times the specific heat of that substance. All right, so this is just putting in your notes the difference between joules and calories. So the standard metric unit for heat is joules. Okay, the second common unit of heat is calories. And this is the conversion. So I guess this is probably the most important part. If you have to convert between joules and calories, you do need to know that 1 calorie is equivalent to 4.18 joules. Okay, so that's how we're going to relate these two units to each other. So bottom line, there's two different units for heat. There's calories and joules. You're going to see both in practice problems, so just get used to it. All right, so we're going to finish up this lecture with a couple of examples using the specific heat capacity, or specific heat equation, I should say. So we're going to do 3 examples, and we're going to figure out how much heat was absorbed or released given the information. So the first example is how much heat is absorbed by 250 grams of sand as it goes from 150, I'm sorry, not 150, that should be, again, the formatting got mixed up, so this should be degrees. So as it goes from 15 degrees Celsius to 32 degrees Celsius. And remember, we also need to know the C, the specific heat of sand, and here we're given it in calories, 0.19 calories per gram degree Celsius. Okay, so anytime we are quantifying heat, the first thing we need to do is write down our equation. Q equals M times C times delta T. Okay, I always say Q equals MC delta T. All right, that's my little, shortcut. I know it's in a different order than the previous slide. It had delta T in the middle and C on the outside, but as you know from math, it doesn't matter which order it's in because it's all multiplied together. Okay. All right, so we have to, next, after writing down our equation, we need to identify the variables. So remember, M is mass. Mass is always in grams. So our mass here is 250 grams. So 250 grams is going to go here. Right. We know our specific heat. That's 0.19 calories per gram degrees Celsius. And then last but not least, we need to know our change in temperature. Okay, so that means we need to know our final temperature, all right, which we do, that's 32. And our initial temperature is 15. So 32 minus 15 is 17. Okay, so we need to multiply that by 17 degrees Celsius. All right, so let's do the math real quick. 250 times 0.19 times 17 is equal to 807.5. All right, now what, we always need units, okay? Every single number that you write here in chemistry must have a unit. So let's figure out our units. It's easy to figure out the units if you look at each of the units that we have for the numbers and look and see if any cancel, right? So for example here, this is calories over grams degrees Celsius. So this is kind of like, you know, these two are on the bottom of a fraction. So if they are on the top, all right, of something else, then they're going to cancel. So in fact, let me just kind of show you if we did the math with just multiplying the units together, we'd have grams, calories, degrees Celsius on top, right? And we'd have grams, degrees Celsius on the bottom. Now, if you do your math canceling skills, grams is on the top and on the bottom, right? And so is calories. Calories is on the top and on the bottom. So those guys cancel too. So what are we left with? We are left with calories. And so that is our final unit. Okay, we'll circle or box our answer so the teacher knows exactly which one is the final answer. And there it is. 807.5 calories were absorbed by 250 grams of sand as it went from 15 degrees Celsius to 32 degrees Celsius. Let's finish off with two more examples. So again, remember, we are using our Q equals M times C times delta T equation here in order to figure out how much heat is being absorbed or released or transferred from objects. All right, so let's take a look at the next example. It says gold has a specific heat of 0.218. All right, so specific heat, that means that is our C component of the equation. All right, so we know C. How many joules of energy, right? So how many joules, that's our Q, are required to raise the temperature of 15 grams. Grams is our mass, all right, from 22 degrees Celsius to 85 degrees Celsius. So there, in degrees Celsius, is our temperature, right? So that those two are going to factor in with our change in temperature. So let's put this all together. Q is what it's asking for because it says how many joules. You have to always look at the question being asked. Always, always, always go back to the actual question being asked. Three little words. How many something, how much something. Always go back to those three words to figure out what you're solving for. So here we're solving for Q. All right, we know our mass is 15 grams. Right, and we're going to multiply that by our specific heat, which is 0.128 joules per gram degrees Celsius. And then we're going to times that by our change in temperature. So our final temperature is 85. Our initial temperature is 22. We subtract those two, we get 53. So our change in temperature is 53 degrees Celsius. Okay. So if we plug those into our calculator, 15 times 0.128 times 53, we get 101.76. And again, if we cancel our units, grams on top, grams on the bottom, degrees Celsius on bottom, degrees Celsius on top, this time we're going to end up with the unit joules. And it matches what it's asked for, so that's perfect. Okay, So we'll circle it so the teacher knows what's our final answer, and we are good to go. All right, so let's take a look at our last example. It says if 335 grams of water has a decrease in temperature by 6.96, again, that should be a degree sign, degrees Celsius, how much heat was transferred? Liquid water has a specific heat of 1 calorie per gram degrees Celsius. Okay. All right, so this is worded a little bit differently than the two that we've seen before, but it's still asking the same question. How much heat? Those three little words. How much heat? And so that is going to be our Q. All right, so Q equals M times C times delta T every time. Okay, so let's take a look at our variables and figure out what is what. So 335 grams of water. Remember, grams is mass, so we're going to use that for our mass. 335 grams. Okay. C is our specific heat. We're given that here. Specific heat of water is 1 calorie per gram degrees Celsius. And last but not least, our change in temperature. Now here, a change in temperature is actually already given to us. Like, we don't have to subtract this time because it says the water had a decrease in temperature by 6.96 degrees. So that's kind of, easy to use because we don't have to do that extra subtraction step. We've already know it's being decreased by that much. That is our change. So we're going to use that 6.96 degrees Celsius as our change in temperature. So if we plug that into our calculator, we get 2,331.6. And again, if we take a look at our units and see which ones cancel, we have grams on top, grams on the bottom of a fraction. We have degrees Celsius on top and degrees Celsius on the bottom of a fraction. So again, we're left with calories. So that must be our unit. Okay, so we'll circle answer so teacher knows which one it is. All right, so 2,331.6 calories are transferred from the water as it decreases in temperature by 6.9 degrees Celsius. All right, so hopefully that made specific heat and the specific heat equation a little bit more clear with lots of examples. If you need to go back and pause and re-listen to any part of this lecture to kind of understand it clear, please go back and do that. That's the beauty of video lectures. You can pause, go back, rewind, and listen to again.